Okay, let's get this party started. It's 1600 hours. Today, we're fortunate to have Professor Benjamin Recht visiting us from Berkeley. And fortunate for me, Ben has a bio on his website from which I will now read. Ben is a professor in the Department of Electrical Engineering and Computer Science at Berkeley. Previously, he was an assistant professor in computer science at University of Wisconsin-Madison. His BS is in mathematics from University of Chicago and an MS and PhD from the MIT Media Lab. After completing his doctoral work, he was a postdoc at the Center for Mathematics of Information at Caltech. Therewith starts the second paragraph, which is about his awards.
Oh, man.
These include Early Career Award for Scientists and Engineers, Alfred P. Sloan Award, 2012 SIAM MOS Lagrange Prize in Continuous Optimization, 2014 Hamon Prize, 2015 William O. Baker Award for Initiatives in Research, fascinating, and 2017 and 2020 NeurIPS Test of Time Award. So 2017 was the first time they ever gave out a NeurIPS Test of Time Award. It's an award you get if your paper 10 years later still seems to be good. Because sometimes, you know, people are excited about a thing and then 8 years later, they're like, oh, why were we excited about that? But people remain excited about Ben's work. He has served on the editorial boards of JMLR and Mathematical Programming. He co-founded the Conference on Learning for Decision and Control. All those things are true. So Ben is multivalent, active in a variety of fields. Hero to those of us who enjoy iconoclastic truth-telling, and has become a fan of history, which is one way of warning you that I don't exactly know what Ben is going to talk to us about today in steampunk data science. It could be machine learning, could be optimization, could be history, could be something else entirely. Before I start, let us thank our hosts, which include the Data Science Institute and also Mark Hansen, who's hosted us here. We've hopefully drawn a very diverse set of attendees. Some of you might self-identify as data scientists or data scienticians, myself included. Anybody here from DSI or think of themselves as a data scientist or machine learner? And probably I shared it with some historian friends. Anybody here who self-identify as a historian? Thank you. And we're being hosted in journalism. Anybody here self-identify as a journalist or a journalism student? Hooray. Okay, so I'm sure that Ben will entertain us all. Thank you, Ben, for making time to tell us about steampunk data science.
I meant to update that webpage that Chris read because I've been sending out a bio that just says that I'm a professor of electrical engineering and computer science at UC Berkeley, and that's about all I've got right now. I'm in the middle of a identity crisis, trying to figure out what I'm doing next. And through that identity crisis is reflected in this talk, a lot of the identity crisis. So a couple disclaimers. This is my second time giving the talk. The first time was like 4 days ago. It's okay. I feel like it's gonna be better this one. You guys get this better iteration, but it's as Chris said, it's my first foray into history. So there's one equation. See if you can spot it. No theorems to build on yet. I was speaking with Mark at the beginning. At Berkeley, folks like people who use new theory oftentimes decide that they're applied statisticians later in their career. That was a path that was available to me. But then I decided, why not just become a historian? That'd be new. So we'll see what happens. If it doesn't work out, there's always teaching applied stats. So I feel like I take it over from Binu at some point. Okay, there's my disclaimers. So what is this talk about? This talk is a first in what I hope to be a series of things that I will write about, broadly speaking, discovery and how in the 20th century or so, we settled on means of finding what works. When I first started looking into this, I thought I was going to be doing a little bit of an investigation into the history of statistics. In some sense, I am, but it turns out there are a lot of great books that I will recommend to people who are interested in the history of statistics and how it arose. I've been reading a bunch of them and really how it really coalesced as what we think of statistics in the 1800s, but wasn't really formalized until the 20s or 30s. And then I think really everything kind of got locked in and is what we would say today. And then something funny happened after 1940 where it became a bit more of a ritual. This is always something that we find at I'm sure the folks in the statistics department find this here. We think that statistics should be about critical thinking about data, but oftentimes statistics is a crank turning to get a p-value. And there's a little bit of the way that it gets used and the way that we wish it was used sometimes diverge. And especially in applied sciences, because applied scientists are not interested in making statisticians happy, but they are interested in getting their papers published, they maybe go a little bit more into that ritualization than perhaps the thinking about the data in a statistically critical way. What I was interested in figuring out was like, what happened before there was statistics? What happened before everybody knew what a null hypothesis test was, or at least how it might be executed? And the example I'm going to talk about today, which I stumbled upon, was the discovery of vitamins, which happened much later than I expected. It happened in the late 1800s, early 1900s. And I want to talk about how that discovery happened. And it was a haphazard path. And I want to talk about what lessons we can learn, perhaps, as data scientists from that discovery. I also want to say that there's a lot of beautiful clip art in this talk that was made by my graduate student, Paula Gradu, using DALL-E 2. So DALL-E 2, an amazing graphics generator for your future talks. All right, so we start the discussion in Wisconsin. Wisconsin, I spent some time there. Hopefully everybody knows, is the dairy state. They have their football team is the Cheese Packers, and they have delicious cheese curds that are available at any fine rest stop that you hit in Wisconsin. But actually, it's interesting that Wisconsin became the dairy state through a very concerted public-private partnership between the University of Wisconsin and the state and the people of Wisconsin. Because early on, when it was up until about 1880, Wisconsin was actually mostly making wheat, growing wheat. They got hit by a wheat blight, and further Western expansion ended up creating competition. Turned out it was a little easier to grow wheat in Iowa, and then subsequently that even moved more to the south and west. And so now there was some thought about how to actually transition the products that Wisconsin could create right around 1880. There was also a big immigration of German folks from New York who were dairy farmers, and so partnered with the university and the state, there was kind of like this big push to create this new dairy industry. And by 1915, Wisconsin produced more dairy than any other state in the country. So one other thing to mention is that the University of Wisconsin was a land-grant university, so that was actually part of its charter, was to try to facilitate such things. So it's one of the great successes of the land-grant program was this creation of a dairy industry. So this fellow, Stephen Babcock, has a marvelous mustache, but is also probably the most influential faculty member. He's up there, at least, among the most influential faculty members ever at UW-Madison. He has a bunch of buildings named after him. And he's moved to Wisconsin from New York to chair the agricultural chemistry department in 1888. Interesting that there had a department of agricultural chemistry. It wasn't really an obvious that would be a thing. And if you go to Wisconsin now, most of the chemistry and biology is still in the agricultural school because of this history. So agricultural chemistry was concerned with many different things. One of the main things was nutrition. And in about 1888, the only thing that people really cared about was protein. And they discovered protein in the early 1800s. Protein are just apparently carbon chains that have a lot of nitrogen sticking off of them. So you can test for nitrogen. And the main idea was that if you eat enough protein, you're going to be healthy, which is, I think, for people who have done Atkins, I think it's still a common belief. And so this is a reprint from a famous nutritionist in Atwater. This is kind of like his table of data about how much, for 25 cents, how much protein can you get? And I think this just means you can eat a lot of dried beans if you're into that kind of thing. And there's no need for fruits and veggies, right? Because they're very low in protein. And that was the predominant view at the time. people sort of understood that you needed minerals, and they usually figured that out by studying food ash, which is you look at the waste material and you look at the content of the waste material, and that was the stuff that wasn't burned. So they found salts and minerals. So they thought that was important, but they didn't really know much more than that. Again, this is in 1888. Now, Babcock was famous for saying that cows can't live on coal, because if you look at coal, it would have passed a lot of the tests that people were using to test protein content. It has a lot of nitrogen. If you just look at the chemical components, and it burns, it looked like it was a good store of energy. And Babcock knew that was ridiculous. He knew we were missing something. He'd also grown up around farms, and so knew that it's complicated to figure out the right way to raise cattle. So he pitched his dean on an experiment. They were going to get some cows, and they were going to feed them different diets. And then based on those diets, they would know how to optimize the nutrition of dairy cows in Wisconsin. And the dean said no, which is this interesting thing. I'm not sure how many people have to ask their dean for permission to do stuff anymore, but apparently that was the etiquette at the time. We're going to see the mean deans keep coming up in this talk. So they said no. Babcock went on to do other things. In the process, invented something called the fat test. The fat test is a very clever, simple thing that you could do to test the fat content in your milk. And this allowed consumers to check what the fat content of the sellers were. So this actually kind of stabilized the dairy market. It also allowed farmers to test which cows are producing the best milk, breed selectively. And it made Babcock like the most famous professor in the state. And he would go to the agricultural congresses and answer questions and do all this sort of stuff. So by the time he retired, he had enough clout to do his experiment. And so Babcock went ahead with his experimental framework and went and consulted his book on applied stats. And so this didn't exist, but let's say, what would he have done? If instead of 1905, it was 2005, what would he have done to figure out how to do this experiment? He would propose some clear outcome for what it would mean to have one diet be better than another. Then he would randomize subjects into treatment and control. That's what you have to do. And you would compare the average outcome in the treatment group to the average outcome in the control group. And maybe you would correct for some confounding variables of some kind, if you're into that kind of thing. And you would declare significance if the p-value was less than 0.05. And then if that was the case, you send your paper to Science or Nature. That's not exactly what happened. And we're going to see now as we start to go through this process, it was a lot more complicated. It was a lot more complicated. So in 1907, the dean allowed, Babcock had actually had to retire, but he had hired a bunch of other faculty members, and they were all really keen. And they got some people from animal hub. There was a department of animal husbandry at Wisconsin. That's no longer there, but at the time they had one. And they got these cows. They got 16 cows. They partitioned them according to weight into 4 groups. And then they fed one group corn, one group wheat, one group oats, and one group mix. Not clear who's, they did do, you could say that the partitioning was kind of random, but there's no clear control group here. It wasn't really clear which diet was best or what was the best thing to do. And they set off growing these cows. They had them, they tried to breed them, they tried to get milk from them, and so on. Now, as you might imagine, it takes a long time to grow cows. So in the process, this fellow whose face is unfortunately blocked here, poor McCollum, but that's all right. This is Elmer McCollum behind the Zoom window there. McCollum was one of the assistant professors who was hired actually explicitly to be on this project. He was hired to be on the project. He had been reading a bunch of papers from Europe, and the European papers said, we're working with rats, trying to do nutrition of rats. And he tried to convince, everybody on his teams, like, if we had rats, we could grow them much faster. Also, they're much less picky eaters, so we could feed them anything. And we could really get to the bottom of this much quicker. Now, as you might expect, the mean dean comes in again. He goes to ask the dean, I should be able to start a rat colony. I bet you I'd be able to outperform this cow experiment. And the dean said, if the people of Wisconsin learned that I let you raise vermin on this campus, they would have me arrested. And that was the end of that conversation. But McCollum had grown up on a farm in Kansas, and his parents had paid him a penny for every rat he could catch. And he also knew that the barns where they had the cows and the horses had a lot of rats. And so he went and trapped some. He went and trapped some and tried to start a rat colony that way. And he gathered a bunch off the campus. It's funny, the dean didn't want his campus infested with rats, but he was just in denial. There were a lot of rats on campus. The one problem McCollum ran into is that barn rats are actually kind of savage and hard to feed and keep. So he wasn't deterred. Instead, what he realized is he could go to Chicago and buy some fancy pet rats, which is what he did. And he took them back, started a lab rat colony, and started to investigate what happens when he fed these rats different diets. And again, for the first 2 years of this project, did it in secret. I think the other little fun little fact here is actually that McCollum's rat colony eventually became a private rat breeding center. So they're still one of the biggest wild type rat farms in the country for lab research is in Madison. Very influential. So with his fancy rats, he went about trying to figure out how to do experiments. And this is where we start to dig into some data. This plot was one that McCollum had read. It was by Watson and Hunter. This was two researchers in England. Here they fed baby rats either bread and milk, which is the thin line, or they fed them oatmeal that was cooked in milk, which is the thick line. The arrows denote deaths of the rats. And what you could see is that the bread and milk was really good, and all the rats grew and became healthy adolescent rats, whereas for whatever reason, they were unable to be sustained on porridge. Actually, this is complicated and a little bit hard for me to even understand. So what is bread? I think that's one of these funny things. So I'm not sure there's much we could take away, but whatever is in their bread, I feel like bread is not a universal thing. Everybody has different things that they mean by bread. And so whatever was in their bread was good. Whatever's in the oatmeal was lacking something and killed the rats. But McCollum was inspired by this kind of work. McCollum was also trained as a chemist. And so rather than having these kind of like abstract, or well, not abstract, but hard to narrow down foods to give the rats, he was synthesizing these weird diets to feed them. And so he created the synthetic diet. Let's look at this. I should get my tables. So we had two different diets. He had one diet where the rats received this bunch of inorganic compounds, a bunch of organic compounds and some inorganic phosphorus, because he knew that we needed phosphorus to live. And then the other one, he added some hydrolyzed beef fat to make it tastier. And he concluded that actually tastiness or palatability was actually the most important point. And that's really the key to nutrition. And I love this quote at the bottom, where he said that what he ruled out was the lack of certain organic complexes in food, which the body was not able to supply through its own synthetic power from the materials at hand. He said he ruled that out. That was not the cause of malnutrition, which, as we'll soon see, was completely wrong. That's completely wrong. That's, of course, what's actually happened. We know that we have things, which are called vitamins, that we can't synthesize and we have to eat. So it was amazing that in the first paper, when this was published, with all of this data in this first paper, he concluded that there's no way that something like vitamins could exist. And what I love about this table is that, first of all, it goes by dates rather than days. He had no plots. He had a list of different rats. So these are two different lots of rats. In this one, he decided to change the protocol halfway through, where at one point he left out the phosphorus from the ration at one point. And I think he was trying to do something else up there. But it's this weird collection. And there are other tables in the paper of about a dozen rats where we're supposed to kind of get some inference from these time series. But he also has other qualitative data outside the table. So it's very hard to suss anything out. When you plot these, for example, I could ignore this yellow column, which does the weird protocol change, and just plot the average of one lot versus the average of the other lot to see what the growth rates look like. You see that the black here was black is lot 2. This is the one that got the tasty food. White is lot 1. This is the one that got the untasty food. And McCollum concluded that lot 1 did a lot worse than lot 2. But if you are staring at that like I am, it's hard to see that there's a difference. I tried to figure out how I could compare them. I could compare the total amount of growth, perhaps, and do a Welch's t-test. That came out. I don't know what I would do. I'm not quite sure how I compare these growth curves. So whatever the case, he presented this data, presented this argument. It's very confused to me. He clearly got the answer wrong, but we'll see that McCollum redeems himself shortly thereafter.
The average is over the live rats or over all rats?
Over the live rats. Actually, so here the first lot he only let grow to 70 days and then he killed them all. It's also great. He's like, they're not doing well, I'm going to kill them. And then the second one, the rats they all lived to 106. But there was this one where he messed up the protocol. I left them out. He's doing all sorts of things here. Let's go ahead. Probably the smartest thing McCollum did at this point was he hired a lab assistant named Marguerite Davis. I do want to tell her story because she's a remarkable person who that's also a little bit of a mysterious person, was kind of kept to herself a lot. But Davis got her bachelor's degree at Berkeley, wanted to be a scientist, but her mother passed away. She had to move back to Madison to take care of her father and was bored, tried to find some work and got referred to McCollum. They hit it off and she started running his lab and running the rat colony. And from there, it went from some weird inept experiments by McCollum to these amazing, much more detailed, much better cataloged experiments that we'll see in a minute. And McCollum himself always credits Davis for just transforming their ability to do science. So it's a really interesting figure. She went on to run a different rat laboratory at Rutgers, but it's very hard to find any information about Davis. It's also, I bring her up also because this is the only woman who appears in the earlier part of the research at Madison. And like McCollum had a hard time even getting her paid. It's always good just to reflect on things were different in lots of ways. It wasn't just lack of statistics. All right, so let's press ahead. McCollum had published his paper. It was read by some of his colleagues at Yale. He had done his previous work at Yale. And these guys decided, well, look, McCollum has these diets. Why don't we do a little bit more? Why don't we see what else we can pursue? And so Osborne and Mendel went and fed rats a crazy number of diets. They have a 200-odd page monograph on different diets you can feed to rats. And one of their key insights, which made it really helpful, was they found data by a fellow named Donaldson, which is plotted here, which is what is a normal growth of a rat. Donaldson grew about 10 rats, averaged out their weights, give you a max and min, and now we have a normal curve of rat growth. And so once I have this normal curve of rat growth, I kind of know what I should be expecting and can compare a variety of things. So here is a plot from Osborne and Mendel's work where this is where they proved McCollum wrong. They found that you can get rats to eat diets that were very tasty to them, but that they could not grow. So here we have, I really do like this. I don't really understand. On the same axis, I think it is right, the amount of food consumed. They were plotting the food consumed. They're plotting the body weight of the rat. They're plotting the normal growth rate of the rat, and then the diet. And here's one where they ate a lot because it had this protein-free milk, which was made by somewhat complicated process. Fortine is a kind of protein, and they found that this was not enough to sustain the life of the rat. Another great chart, which I love, which also very ended up being inspirational for McCollum and Davis, was they would do these things where you would cross over the diet at particular times. So you have first here a mixed food diet, and then they go to a purified food diet, and you see that the rat grows. And as soon as they switch to this very purified diet, the rat starts to stop growing, actually starts to lose a lot of weight. And this monograph is filled with charts like this. Lovely, hand-drawn, beautiful charts. So Hopkins was a British researcher, saw this paper by McCollum and Davis, realized that he had kind of done the same experiment already, but hadn't gotten around to writing it up, and decided to publish this figure. Now, this figure is another beautiful study. The white dots are fed only bread. Again, we don't know what bread is, but they're fed only bread. The black dots are fed bread and a tiny, tiny amount of milk, just a little bit amount of milk. And you can see that the black dots grow a lot faster than the white dots. And at day 18, he crosses these guys over, swapping their diets. And now you see that the ones that were being fed milk stop growing and eventually start to lose weight, whereas the ones that were not fed milk start to grow. And that was their, this is now plotting because perhaps because he was British, he was actually plotting averages. The previous slide was a single rat. It's actually good to compare this. This slide is one rat. All of the papers in Osborne and Mendel are just single time series of the life of rats, single rats. This paper by Hopkins actually had averages, but no error bars.
Why did you say because he's British?
I'm wondering if he was hanging out with some of the other statsy-ish, like maybe he knew Gossett. I don't know. I was just like, there, scientific communication is much slower. So it's not clear if he had other influences with early British statisticians. But he's plotting an average here. Also, several slides ago, I showed you that one with porridge and bread, also averages, also British. So I'm not something about what they thought was okay or acceptable. What's cool about this Hopkins paper is he has an appendix. And while he doesn't have the entire data of the 8 rats for each of these dots, he has all of the weights at this point, all of the weights at this point, and all of the weights at this final point. And so what I could do is just take, I entered them into Excel by hand, which I know is not what I should have done, but I can fix this later. The weights at these 2 points and at these 2 points. I can make a more modern representation of what we would see here. So now instead of, I had to pick some kind of way of condensing everything down to one number. So I decided to do percentage of growth from day 0. And you see that without milk, the rats grew less than 20%. Every rat grew less than 20%. With milk, every rat grew more than 60%. The lines, the error bar lines here are just the extremes of the data. So, and the extremes do not overlap. And would anyone care to guess what the p-value associated with this figure is? You're supposed to ask which test, but it doesn't really matter. It's 0, right? It's clearly 0, whatever number you want to assign to it. It could be by chance. I don't know what null hypothesis you want to presume here, but it's a surprisingly robust result. So something happened. What did he do? Something is in milk. We don't know what it is. Something's in milk. What McCollum and Davis did after seeing this result by Hopkins, also kind of in parallel, was because, again, McCollum was a chemist, tried to make a purified diet that would have the same effect. And this is an example of a purified diet that has the same effect. It's amazing that I'll show you, I don't know why I need to show you without them. Here we go. Here's the same plot. Here is what's actually happening. For the first period, when the rat is young, they feed them salt, protein, and fats, and a little bit of carbohydrates. For the second period, they remove the fat. And what happens, what you should be able to see in the second period, is eventually the rat weight plateaus. Again, now we're back to one rat. This is one rat. So the rat's weight plateaus, they stop growing. Then in period 3, they add the ether extract of egg. Honestly, I read ether extract, and that's where the steampunk idea came from. Because really, there's nothing more steampunk than ether. And what does that mean? That means that they took an egg yolk, they put it in this chemical called ether. Ether will dissolve things that will extract from fat things that are dissolvable in fat. So you shake it up and you get a precipitate at the top. That's like all the stuff in the egg yolk that dissolves in fat. They took that stuff, whatever that stuff was, and they added that to period 3. And the rat started growing again. What's that stuff? They called it fat soluble A. And it's what we now know as vitamin A. Possibly some vitamin D in there too, because vitamin D is in egg yolks and is fat soluble. But definitely because of the symptoms this was curing, it's pretty clear that this was where vitamin A was first extracted and discovered. And it's amazing, right? It's just like it's a single time series with clear interventions. To be fair to them, they had 5 time series. They had 3 males, 3 males and two females. And there was some, but the entire paper was based on that. So before I move on to finish the story about the discovery of vitamins, the one thing that we hopefully was clear as I was like talking our way through these graphs, all they were trying to do was study growth. And let's just step back into the present for a second. What is the right way to measure, to compare growth curves? I have 2 curves that are measuring the growth of an animal, or maybe the wear on something, or or the rate of infection, or lots of things, right? I want to compare these growth curves. How do I compare them as a statistician? So everybody's friend George Box has a very nice paper on this. And I feel like Box, I have not been able to find anybody doing anything better. Box really sets out most of what people do today. And the answer was either I could build statistical models of what the growth is and run a test based on that, or I could pretend I have statistical models and do some kind of ANOVA, or I could just decide in advance on some summary statistics and call that my growth, like what I did when I said percentage of growth. And what's amazing is if you keep looking, especially if you look in the biomedical literature, there's no specified rule as to how you're supposed to compare growth. So I find this, the reason I'm bringing this up is that McCollum, Davis, Mendel, Osborne, Hopkins, all these folks, they were looking into, they were cared about growth. Growth was clearly the thing they wanted to study to understand nutrition. And yet they didn't have a clear target, a clear answer, a clear hypothesis test. But even now, 100 years later, we still don't really have good advice. I don't think we would have good advice for them as to what to do. It's not clear that we would add value using data science tools beyond what they were already exploring. We can have a conversation about whether or not you agree. Think about it as I wrap myself up here. Okay, so Dave, do you know what time is it? Does anyone have the time real quick? Perfect. Oh, I have plenty of time. Good, good. I think Bucks was at Wisconsin. Yeah, yeah, yeah. At least at some point. Yeah, at least at some point. He brought averages to Wisconsin. That's why we got them there. So there, what I do find a little bit funny is like McCollum and Davis had started publishing papers on their rat colony before our cow project finished. Well, let's come back to our cows. It took them 4 years. Right, all of these rat experiments were happening over the course of months. The single grain experiment took 4 years. Here are the cows. These are the wheat-fed cows. It's a little dim on the screen, but you can't really tell by looking what the difference between the wheat-fed cows and the corn-fed cows were. It did seem like the wheat-fed cows were more sluggish. The really remarkable result they saw was the cows that were fed wheat had, these were all female cows. Or I guess they were heifers, and then when they had offspring, they were cows. Boy, I should know this, having lived in Wisconsin. But the cows who were fed wheat, all of their offspring died either in stillbirth or very shortly after being born, which was sad. So clearly there was some kind of nutrient that was not being supplied by the wheat. All of the corn-fed cows had good offspring, and the milk had different fat contents depending on the diet. So the corn-fed had less fat than the oat-fed, and the wheat-fed had almost no fat content whatsoever. So the wheat was really a poor choice of the diet. So they didn't publish this in Science or Nature. They published this in PNAS, which is obviously that's where you go next. But it took them a long time to actually get to that point. And by this time, the paper from McCollum and Davis had been published by the time this was published. So McCollum was right. Maybe you want a smaller model. Now let's go to the other side of the world. Back to 1888. So we wrapped up our time in Wisconsin. We discovered vitamin A. In discovering vitamin A, what was required there? It was basically scientists being really stubborn until they were allowed to do the experiments they wanted to. And once they were allowed to do these nutritional experiments that Babcock had envisioned in 1888, very rapidly, they figured out how to hone in on nutrition and find what we now know as vitamins. By a completely different path, vitamins were also discovered in the Dutch colonies that are now Indonesia. So this fellow, Christian Eichmann, another amazing mustache, I had to throw in that picture too, was a student of a fellow named Koch, who hopefully people have heard of Koch's postulates, was the guy who came up with Koch's postulates. In the 1800s, believe it or not, that's when we figured out germ theory. It took a long time to get there. So the things that we did not know in 1800 always amazes me. But one of them was germs. We didn't really appreciate germ theory. Koch really created a nice conceptual framework for thinking about germs and infectious diseases. And Eichmann was a student of Koch and was sent to Jakarta, which was called Batavia, or there was a colony called Batavia right there in 1888. He was sent there to study a disease called beriberi. He wanted to find the root cause of beriberi. Beriberi is this like paralytic disease. It was really bad in kids. It's a pretty horrible for anyone who had it. And it was running rampant in Asia. Since Eichmann was this devoted disciple of Koch, he was sure that it was an infectious disease. And one of the things that Koch's postulates say is you have to be able to isolate the agent and then give it to another organism. You have to be able to find the thing that causes the disease and pass that on by giving that to another organism. So Eichmann was like, I'm going to extract the blood from people who have beriberi, and then he tried to infect rabbits, he tried to infect monkeys, he tried to infect chickens. The only one that worked was chickens. He was able to infect chickens, or at least it appeared he was able to infect chickens with beriberi. The biggest complication being that the control group and the treatment group had the same incidence. So he only gave the blood to one set of chickens. Somehow these other chickens were getting sick. Now, we're about to find I'm about to tell you the most amazing natural experiment to ever happen. All right, here it is. What had happened? How was this possible? What Eichmann figured out was something amazing. Here's what happened. This is a sad beriberi infected chicken. They get this paralysis of their neck, and they can only look up. The person who had been tending the chickens had been feeding them the leftover rice from the mess hall, which was at the kind of like military campus where Eichmann was. The chef at the military campus decided that once he found out about this, he's like, you cannot feed this military rice to your civilian chickens, and stopped giving that's a quote by Eichmann, that stopped giving the rice, this rice. Now, the difference between the rice that was fed to the military barracks and the kind of rice that you could buy for cheap was the rice was polished, or what we know as white rice. Because I hate to say it, I know it's empty calories, but it tastes better. So the white rice was more popular, and that they wanted to conserve that for the military barracks. And so they were forced to feed the chickens brown rice again. And all these chickens who had beriberi were cured. And so there you go. Now you have discovered, they went and figured, it was clear to Eichmann, there was something in the rice. There's some, or at least something about the rice. Now, Eichmann, this is another good lesson for us all, because he was trained by Koch and because he thought everything was germs, he was convinced it was still a germ. And that perhaps that when you polish the rice, you're making the white rice susceptible to some kind of other growth. Or maybe, he wasn't sure, but he knew that it was something about the rice and the white rice, but it was still a germ. And honestly, he won the Nobel Prize, and we'll talk about that in a minute. He won the Nobel Prize, but I don't think it took him a long time, 30 years, to figure out that it was actually a vitamin. And the vitamin in this case is B1. The vitamin that's in the rice husk, that's not in the white rice, is vitamin B1. And so what happened with beriberi is Eichmann observed this, they call it polyneuritis in the chickens, which is beriberi disease. Goes around searching for the cause, and there's yet another beautiful natural experiment that happened that was communicated to Eichmann by this fellow Vorderman, where they saw certain prisons were feeding prisoners white rice and certain brown, and there was no beriberi in the places where there was brown rice, and there was rampant beriberi in the places where there was white. So again, seemed to confirm that this was true in humans. And it wasn't until 1901 where there was a really nice experiment showing that really it's the rice bran itself, where Grimes just fed the chickens meat and these shavings from the brown rice. So it couldn't be that the white rice was somehow like creating an infection. There's no white rice involved at this point. And he knew, there's a great quote by Grimes where it's like, there is something essential to growth and inside the rice bran. It still took a while to convince everybody. There was a experiment by Pohl that showed that you could cure beriberi with mung beans. Again, mung beans also have vitamin D. But again, it wasn't really until about 1909 where people were really 100% sure that this was a deficiency disease. So like a good 20-year period of hashing it out. And so later, Casimir Funk was the one who really determined that there's this vital amine. Casimir Funk also at the same time discovers that there's also a vital amine in citrus. which we may have known for a long time because of how to prevent scurvy, but he found a similar kind of chemical property both in citrus and in rice. And he came up with this term, vitamin. And finally, our friends from Coleman Davis back in Wisconsin were able to just very rapidly with their rat experiment show that there was this water-soluble compound that they could find in the brown rice, just extracted in a very similar, now for a water-soluble compound rather than a fat-soluble compound. They extracted this and were able to do their same experiments with rats, confirming water-soluble B. So now we have A and B. And what's amazing about vitamins, I mean, this is one of these completely transformative events where there were all sorts of diseases that affected people that were caused by malnutrition. Vitamin A deficiency is called night blindness. And that was the one that they were curing the rats of. There's beriberi, which is a B1 deficiency. Here's all the vitamins. Scurvy, which actually was known somehow to be cured by limes or lemons, but it was, again, not known to really be a deficiency disease. Later, so vitamin D and vitamin D3 were a little bit later, but again, now people could actually see these things. Rickets was cured by vitamin D. Vitamin D was also discovered at Wisconsin. Vitamin D also managed to make Wisconsin a ton of money because they figured out how to put it into milk and they patented it. So lots of good state university research. And finally, there's also pellagra, which was cured in 1937. So amazing finding. Turns out you need more than protein. You need these vitamins. And just by having these, this is not saying, again, the takeaway from here isn't that everybody should eat multivitamins, but that you need some kind of diversity in your diet beyond pure protein. And with enough diversity, you can cure diseases that were plaguing large parts of the world. So what are our takeaways or my takeaways? I'm still working through this. I love this example. And it's beautiful how many different things you can see and how many things I think it teaches us about how we figure out what works. So one thing that I do think is somewhat, to me, it took a while to actually see this connection. So you guys, again, I want a lot of feedback on this. So this part of the talk, you tell me how much is complete BS. So this finding what works in both of these cases, whether it was the folks searching for a cure for beriberi or the folks searching for the optimal nutrition, what they ended up doing, and sorry, this is where I get blinded by my own discipline, they ended up doing something that was much more akin to optimization than just trying to understand natural order. I feel like there's really something fundamentally different about this search for vitamins than, let's say, the contemporary searches for understanding of like relativity, which are happening right around the same time. Right? That was understanding how the world, in some sense, like how nature is, but there wasn't necessarily interventions. Here, there were clear interventions. There was a clear outcome that they had in mind, and they wanted to find some policy, whether it be a diet or a treatment or some other intervention that would maximize the outcome they were interested in. So what's interesting about that is that when we think about randomized controlled trials now, especially in biomedicine, but I would argue also in A/B testing, that is the mindset we have. We don't always say it explicitly. What we're trying to discover is a policy that improves whichever outcome we've specified. And most of the hard work goes into being really clear about what that outcome is and being really clear about what policies we have access to. And of course, there are other approaches. Not everything has to be found by a randomized control trial. And those are some of the things I would actually like to think about as we kind of go to the end of this talk. And let me skip these points because don't need to go into those unless we really want to. Second point, and this one always is a controversial one, but even more controversial. Okay, I'm just gonna pause for a second for the super hot take. Here's my super hot take. My argument is that large effects do not need statistics, and small effects are usually illusory. This is where I get in trouble, and everybody gets mad at me. But I do really feel like this is worth engaging with. I feel like we have got ourselves into this weird space where if we look at these plots, and let's say that these are the benefits in the associated population of interest for some particular intervention. Okay, we have 4 different possible benefits, and these are their shapes. Well, 3 of them are statistically significant. Okay, and 1 of them is not. What's different between the first person, the first benefit in the upper corner, I can't even figure out how to see this on the screen, upper left corner for the folks at home, and the one in the bottom left corner, those look so similar. And really all I did was shift the bump over. Oh, I think one had 0.51 and one is 0.49 in the p-value. Now, I think another candidate for significance would be the one in the top right corner, which is tiny, but consistent and tiny. And those can fluctuate just by changing what the intervention means on a day-to-day basis, right? The intervention or the population changes a little bit, those things can change. Obviously, we want the bottom right. Everybody wants the bottom right intervention. And the problem, the frustrating point about the bottom right intervention is they're exceptionally rare. Finding these results where you get a huge benefit and it works for everybody, you say that doesn't happen. It happened in vitamins. And I'd like to remind us, it did happen, with the vaccine trials. We still have these, and I have other examples. I've been trying to find them. They don't come around very frequently. And certainly more often than not, we see small things. But in the end, we do every once in a while get these things where it's so unambiguous that we do not need statistics to suss it out. Actually, in fact, in this trial, the statistics was most useful for was knowing when to stop. So I actually think statistics has a lot of value, and I think in a regulatory framework, statistics provides a lot of value, but it was one of these things where the most important thing here was just knowing when to stop the trial so that we could actually start to help people. Okay, two more little bullets. I actually think this is less of a hot take, but you guys tell me if it's a hotter one. I think most people who have been involved in statistics and people who have at least been around data science have heard of the reproduction crisis. It's one that's supposed to be shaking science to its core. But are we sure that reproduction crises are bad? So if we go back and look at this vitamin trial, like we know where this vitamin stuff, McCollum's first paper was very wrong. And moreover, like there were other people involved. I didn't even talk about STEP, who made rat trials that were on the right track. They certainly looked like they were getting the right answer, but they're completely unreproducible. So we had these things that were unreproducible, but they led us to the right outcome. This is a bit weird. Now, I don't think anybody here is committing scientific malpractice, and I don't think any of this would have been fixed with hypothesis testing. But I think that this is something that the meta-scientific community needs to engage with, which is that actually we can learn from the mess, and that a lack of reproduction can be informative, even though we should strive to be rigorous and communicate well. I'm not saying that you guys should just throw spaghetti at the wall, but I do think that sometimes we should maybe not expect so much from science to be perfect. And I think that that's something that I thought was an important takeaway from the vitamin study. Number 3 was what people attempted to reproduce and failed. In fact, STEP was someone I didn't talk about, but some people think STEP actually was ahead of both of even Hopkins. So the people who it's also one of these funny things. I don't want to go too much into this politics, but out of all the folks involved here, only Hopkins and Eichmann got Nobel Prizes. So everybody else got left out, and everybody else was very angry about it, but we don't have to talk about that today. But STEP was someone who actually was ahead of all of them, and really had figured out, he had done this thing where he took bread, did an ether extraction of the bread, and then had these two compounds where you have the extracted bread and this ether extraction. And if you just fed them the bread that had its nutrient strain of it, they would die. And then if you fed them the combination of these two things, they would live. But they were dying at weird times that no one has ever, STEP's rats were dying too quickly. So no one's ever been able to figure out what exactly happened there. So complicated. He kind of had the right answer. Not successfully reproduced, and not reproduce. We know now that something was weird in STEP's lab, but he had the right answer. Wild. Here's my last point. This is the last question. I'm not sure if anybody knows that. This is a quote of, well, it's a famous saying of Paul Feyerabend, who was a Berkeley professor who thought that science should have more anarchy. And so if you look at all the different techniques that went into trying to get at vitamins, it's a huge set of investigative tools. We had natural experiments, we had real experiments, real controlled experiments. We had these things that look almost like impulse response analyses that you might do in an electrical engineering lab where you're looking at growth. There was like very clear directed search to try to make these things, try to find the optimal intervention. Sometimes the case studies were more informative than the controlled studies. And so I think rather than a hierarchy of evidence, there was just a lot of evidence. And putting that evidence together and communicating and trying to figure out what happened required a lot of different investigative techniques. And I think that that's another thing sometimes we lose sight of if we try to create some kind of narrow notion of what a good experiment is. And in particular here, like the Wisconsin crew and the Dutch and later European crew took very different paths to get to the same point. One was looking at infectious diseases, one was looking at animal nutrition. And they both kind of got to the same place, even though they were after two very different things, believing very different things about when they started. And I just kind of want to end with a quote from a really lovely book I just read, which is that the meaning of an experimental result doesn't depend on the care of which it was designed, but it depends on what people are ready to believe. That was really lovely. So in the end here, that was the discovery of vitamins. It was a winding path. It was a bit of a mess. It had a diversity of investigative techniques, but at the end of the day, they found these undeniably large effects that completely transformed our understanding of food and our ability to treat a variety of diseases. As far as the future goes, I'm going to just go real brief and I can hang out and chat about these things. The one question I always want us to ask, and I know there's some folks in stats here, some folks in data science here, is the question is what we envision as data science and what we teach as data science, does that inhibit creative exploration? The answer could be no, and that's cool, but I think it's a question that we should ask. Question I have personally, just from my own, something that myself and my group have been trying to think about, is if you think about this kind of discovery as a way of optimizing policies to maximize outcomes, that's something that folks who do reinforcement learning and bandits think about. And also people who do optimization think about. Are there ideas there that maybe could be added to our tool chest that needs to be diverse and creative? And the last thing is I love these experiments where the n was equal to 1. They carry a lot of weight. For people who know the hierarchy of evidence in evidence-based medicine, case studies are almost the bottom. They're like the almost lowest form of evidence. The lowest form of evidence, by the way, is the opinion of experts. So I do whatever's worth. I didn't make that up. I can show you guys that pyramid. But right after the opinion of experts are these case studies. And so I think a lot of times in investigations, like people discount, they say, oh, that's anecdote. I don't think it is anecdote if it's done properly. If you have these interventions that are clear, for example, Marshall won a Nobel Prize for proving that ulcers were caused by an infection. How did he prove it? He gave himself the infection and then cured himself with antibiotics. Wouldn't recommend anyone doing this. I'm just saying that was a very powerful case study. So there is something very interesting about understanding the experimentation when n is 1 and thinking about what statistics look like. The things that you're going to run into, and I would love to chat more with stats folks about this, is everything, all of the lovely independence you get when you do a randomized assignment goes away. And now there's all sorts of new places where confounding can happen, but it's confounding on the scale of you. Anyway, so with that, I'd like to wrap up. Thank you all for listening. Thank you all for taking the time to dig into this history of vitamins. And I'd love to hang out and chat more about any of these ideas and get your feedback. Thank you.
I've just to up the ante on this. Doesn't this mean that the scientific method needs to be questioned?
That's a good question. That's a good question. So what Feyerabend said, and this is kind of what set me down this dark path, is there is no scientific method, which I actually think is kind of beautiful. I mean, I think sometimes I have a 4th grader, and on his first day of class, he had he had science class, and they told him what the scientific method was, and he was also very confused. So I thought that like he tried to explain it and he's like, this seems a little bit arbitrary. I was like, maybe it is. So I think that there is something definitely to the notion that there is a scientific method is very unclear.
So to look at the effect size or n=1 experiments, I think is an interesting thing. I think when you look backwards, it's easy to say this experiment worked.
Yeah.
It's a perfect example of survivor bias, right? Like you forget about the 900,000 other people that tried to do the same thing and came from University of Minnesota who somehow didn't figure it out. I mean, just to think of a Wisconsin joke. But I wonder, like, you know, part of that is thinking about which variables actually matter. And if you define the right variables and have the right set, which you know because of a lot of other failed experiments and or successful ones, that it's easy to make a successful experiment with an n=1. But you didn't necessarily know that as you go in. So as you're saying that most experiments have low effect size, I would argue that's because most of the time we don't know the actual variables. And no matter how good of a statistician you are, if you put in garbage, you get garbage out.
Yeah, I agree. I definitely agree with that. I definitely agree with the it's hard to know what variables matter when you don't know what you're looking for. I definitely agree. I think there's two aspects to the n=1 business. I think if you have these case studies and you stumble into them and they're definitive, we do know. It is one of these funny things where we really do know. And again, I gave you two examples with the vitamins and then also with Marshall and his ulcer. And honestly, I mean, gender and vaccination also were just like 3 case studies with children. It was very sketchy, but like we have a history of this in science. They're rare. I think there's another interesting part about the n=1 though, which I didn't mention here. I think that they're thinking about n=1 as maybe we think about it as the experiments we do on ourselves, like where I am the control group and the treatment group. I want to find what's the best sleep schedule for me. I can't really do that by a controlled experiment because I am the control group, and obviously there's going to be these kinds of correlations. That might be too simple an example, but when you think about how does a doctor come up with an appropriate treatment plan for a patient, and also requires a little bit of experimentation to find what works. There's no way that you can't just take a patient and extract a feature vector and give them take 2 of these and call me in the morning or something, right? It's not like that. There is this kind of individualization that has to happen. And I'm not saying personalized healthcare. I'm just saying that there's an interaction you have with your physician or your psychiatrist or your physical therapist that happens over time. I think thinking about that and thinking about that in terms of protocols is another interesting direction that I think would be worth us thinking a little bit more about how we can make it more systematic.
So I'm curious what this means for this current wave of wanting to regulate AI. And I think we have some historical precedent for that, which you've already discussed, which is basically the way algorithmic research is regulated in medical regulations today. So what does that mean if we, to your first question about inhibition of creative exploration?
Yeah, I think the AI regulation has been an interesting question, right? I don't think we still understand how to do we don't understand quite what it means, right? I mean, I think on the one hand, there's the like data privacy and algorithmic recourse that something like GDPR tries to go after, which isn't necessarily about any part of creative AI. And there, and something that's not on this slide and should be, that's really just a question of values and ethics. And in some sense, that has to happen here too, right? I mean, all of these experiments we're talking about, again, I go back to Marshall with his ulcer. The reason he gave it to himself is there was no IRB board that he had to pass by, right? There's no, I mean, you can come up with some reason why it's not ethical, but for whatever reason, medical ethics says it's fine to do whatever you want to yourself, as long as it doesn't harm others. So that's what he did. That was his quick way through. So I think a lot of these, something that probably should work into this talk a little bit more, and because they were working with rats, one of the reasons McCollum liked rats was also like, no one's going to care what we do to them. It wasn't an ethical argument. It was like, people might care if we're abusive to cows, but rats, no one will care. I think people care, honestly. But that he said, this is what McCollum. But I think that, like, yeah, that question of ethics and how that fits into this story is an important one to really unpack.
Thanks for the talk, Ben. I want to go back to that slide where you were talking about like large. I mean, you don't have to actually go back. I'm just bring us back there.
Okay.
Where you were talking about large sample size studies, sort of not needing any statistics and how that's rare. I was kind of wondering, isn't that a
large effect?
A large effect, sorry. Yeah. Isn't that an argument for why we actually need statistics? Because most of what actually happens in science is not the sort of that.
Yeah. So actually, I think that's where I'm currently at, is exactly what Stephen said, which is, I think that what statistics has done and has been very useful is guiding regulation. I think statistics has been very valuable for guiding, like, how should the FDA decide which drugs to release? And it's hard. It's not an easy question, but they've established, like, you have to pass these hurdles. There have to be, the rate of adverse effects have to be low. The benefit has to be high. And that allows you to both kind of set, maybe they're a little arbitrary, but set guidelines that interface with values and safety, right? And it becomes a regulatory process. Some might argue that's bad because it gives pharma companies the ability to, like, hack. Like, they can hack those regulatory paths. But I think that's, to me, that's what an underappreciated part of statistics is, the ability to add a little bit of rules to a regulatory framework.
Hi, thank you for the talk. I'm from the journalism school, and I study data journalism. I really liked the part about where you said you have to sort of accept the messiness of science, and you should be comfortable with that. I wonder what you think about sort of communicating that messiness to, like, the public, as a journalist, especially when it comes to things like, public health, environmental issues, because there is that messiness there. I think we can see that from, like, how the public accepted, like, the COVID trials and all of that. Like, how do you wrestle with like communicating that to, like, a large amount of people?
Yeah, I mean, most of this talk is a reflection of my own wrestling with exactly that, of what we saw over the past couple of years. So a lot of what I've been working on has been, I mean, it's been hard to, obviously none of us have been able to escape of the COVID supremacy over all of us, right? I mean, it's been everywhere. And certainly when, I started at the beginning, but it continued throughout. I couldn't stop consuming these public messages and trying to understand what people were after, and trying to just see how these, like, scientific ideas got memed, whether or not there was evidence involved. And it was kind of a fascinating behavioral thing. That's really where it clicked with me, is like, this is all kind of social stuff. And what is, there was that quote I had by Collins and Finch, like, what we're willing to believe is kind of more important than what actually is, like, data itself doesn't actually necessarily show us anything. The quality of evidence is always a little bit questionable in any given experiment, and honestly, even in any collection of experiments. And so I wish I wish there was a clear answer for how we're supposed to engage with uncertainty, because especially in times of crisis, no one wants uncertainty, right? It did seem like everybody erred on the side of, that was this whole weird inversion of the precautionary principle. We're just gonna do everything on the side of caution. Whatever it is, we're not gonna think about the harms. This is scary. But yeah, I think it's interesting for the journalists in the room. Like, how the information travels much faster than it did in 1800 or 1888, and it's everywhere. It's everybody's face, and you get a poor guy like Anthony Fauci who tries to. I mean, I don't know. I think at this point he's exhausted, and the man is a little old. I feel bad for him, but I think at the beginning he was trying to give nuanced answers, and everybody would nitpick these little nuanced answers, like, oh, he's lying, or oh, he's saying this, and so that stuff is, there's no win. There's no win. There's no win to nuance. And then there's not really a win to a lack of nuance either, because then if you're wrong, people are like, oh, you said this and it didn't happen. How we engage with that, I don't know if we learned any lessons. I'm frankly worried for the next thing. I feel like the information age has given us far too much access to moral panics. They always used to happen, right? But they make them really fast, and I don't know. You guys have to tell me how to do. Like, this is, I think, the role of the at least you're asking the right question, right? So I think this is the role of everybody who's in journalism school right now, is to figure out how do you grapple with that. How do you grapple with the fact that that information is going to move quickly, whether or not you get on top of it? I don't know.
So thanks for the talk. So I was really interested in, like, sort of, usually nowadays people started to do randomized experiments to understand the effects of causes. But in your story, it's more like they did multiple experiments, started to understand really the causes of the effects. And there was some kind of like innovations and also some like mistakes and like some randomness that like you really discover the vitamin is doing the things, right? So try to understand the effect of the vitamin is one thing, but to understand the vitamin was actually causing the effect was a different thing. So what you're thinking about, like, these many discoveries are really the discoveries of the causes of the effects rather than the effects of the causes. So
yeah, man, that was the question I stayed away from, but I'm glad you asked. I was just, because I didn't want to bring it up myself, because I think that there's a tricky business of causal inference and inferring causes, and I didn't want to get too into it because I really like Dave and don't want him to be mad at me, but I do find that, like, what we expect causal inference or the search for causes to give us is very, very tricky, very murky, and it's not clear that we have tools to do it. Not clear that we have tools to do it. I think that, like, casting, I had this thing where I cast it as we just have an outcome that we like, and we want to find policies that make the outcome go up. That's not really a causal question. I feel like that's what people end up doing, whether or not a cause or effect. I mean, an understanding doesn't have to happen in order to have a policy be improved. This is interesting, right? So I think that there's something to be said for the fact that, what utility are we adding by thinking about cause and effect? What utility are we adding by reading Judea Pearl? He's probably watching, and he's really mad. Well, I want a clear thing about, like, what value is that machinery bringing? I think it's tricky. I always get, and we could do this over some refreshments. I always get confused by what we think we can do with regards to understanding cause and effect and what value that's going to bring, and even asking that question. But I thank you for asking it, because it's one I did want to engage with a little bit.